I'm going to talk a little bit about producing commercial feeds. And I'm primarily going to focus on floating feeds because those seem to be a little more popular these days than the sinking feeds. We can talk about sinking feeds later if we have some time. But basically, here's what I'm going to talk to you about today. So by the time we're done at lunchtime, you're all going to be experts, hopefully. So we're going to talk a little bit about the goals of processing feed, obviously delivering the nutrients to the fish, but there are other things we need to keep in mind. We're going to talk about the basic principles. We're going to talk about basics of extrusion, types of extruders, common conditions, key things you need to think about as you're processing. Give you a little bit of theory, not too much hopefully. And then making feed is all about trade-offs. And we're going to talk a little bit about the trade-offs, and then we're going to talk about some of the challenges. And hopefully by that time the food will still be warm. So we'll go fast. How does that sound? So when you make feed, it's not just about delivering nutrients. Ultimately that's what it's about, but it's about delivering digestible nutrients. And so when you think about extrusion processing, you can produce feeds that are sinkers or floaters, or as one of the previous speakers talked about, slow sinkers. So it's all about how you operate the extruder and the conditions. Typically we think about expansion, at least partially, because we need to have a porous structure in the pellets in order for the pellets to float. But we also need the outer shell of the pellets to be impervious to water. So these are the things that we think about. Starch or carbohydrates are functional sometimes. Sometimes they're not. If there's starch, we want that starch to be used as glue to hold the pellets together. You can use extrusion to sterilize your feeds if you operate at high enough temperatures and pressures. Expansion, texturizing, and then shaping. So when we think about feeds for fish, we think about circular pellets. But how many of you eat Cheerios for breakfast? Okay, that's also an extruded product. Wheaties, on the other hand, which of course is the breakfast of champions, is not extruded. But maybe Cheerios should be the breakfast of champions. So in its simplest form, basically, when you extrude raw ingredients, you basically have a screw, a large auger or a small auger, and basically you have pellets that exit the machine. So it sounds pretty simple. Except for it's not just the extruder you need to think about. You have to have some type of a temporary storage bin, some type of a conditioner. Generally speaking, you need to add more water or steam to start the cooking process before you actually enter the extruder. Some extruders you can actually add steam and water in the process so that you can do a better job of cooking the ingredients. And then generally you need to have some type of a dryer cooler, because you add water in a conditioner and in an extruder, only a little bit of that water is going to evaporate and you're going to have a wet product. And you need to have a dry product in order to have some type of a shelf life. So this is a really interesting picture that Wenger produces on their website. It kind of shows you cutaways of the feed bin, the conditioner, and then the extruder is just a very small portion of that. So another company, Instapro, produces a single screw type of extruder, no heat, no steam, no water injection. So basically what you see is what you get, and it's friction with the screw elements that actually do the cooking. And we'll show you a couple of pictures shortly. But basically any extruder, this is true not just for Instapro, but you've got some type of a location where you dump the ingredients in, you have some type of a feeder, and then you have different locking mechanisms that actually interrupt the flow. So that those ingredients sit and they churn a little bit and they have friction, and then the conveyor flighting pushes this down to some type of a die restriction. So when you're taking a look cross-sectionally, okay, basically what the screw does is purely conveying and mixing. Okay, you interrupt that flow at all, and those ingredients are going to sit there and rub against each other, rub against the walls of the barrel. So when you think about extrusion, you typically have three sections. You have your introduction section, you have your mixing section, and then you have your metering section or your die section, where the most of the heat actually is transferred at that point. So it's not just conveying, though. Within the screw flights, you get random chaotic flow. That's where the mixing happens. The particles tumble over each other. So naturally what happens, the more friction that occurs, the higher the temperature. So if you were to graph temperature over distance, what you would see is a ramp in temperature up until that material discharges out of the die. So, all right, now this is back to the Wenger system. This is an infrared picture. If you take a look, this area right here is the conditioner. And you can see we're adding hot water and steam. This is the extruder right here, adding hot water and steam into the extruder. And what you see is a lot of non-uniformity. Okay? This machine also has band heaters around the conditioner and the extruder, but there's not a lot of uniformity. So in terms of having good control, good temperature control, and moisture distribution, there are a lot of challenges. Now, this is a picture of, I just did this study last week. This is that InstaPro that I was showing you. No water, no steam is added purely due to friction. And we see the ingredients are added over here and about 19 degrees Celsius. So it was room temperature. And then in about a 2-foot section there, we ramped up to almost 160 degrees Celsius, purely due to friction. And then these are the extruded pellets as they were falling out of the discharge. So one of the challenges is you don't have a lot of control here, and so if you get high temperatures, your pellet quality is going to decline. And so this type of a system where you can actually control the temperature and the moisture actually gives you better control over your pellet quality than a system like this, where you actually have to add more water prior to dumping the ingredients into the extruder. So in terms of extrusion, we're going to talk in the next little while about single screw or twin screw extruders. You either have a single conveyor or you have dual conveyors. Basically what happens is not just does the temperature increase, but the pressure increases the closer you get to the die. And same with the twin screw. Basically because you have a little die restriction, a little die hole where the pellets flow out of. And so if you have 10 pounds a minute or 20 pounds a minute or 20 pounds a second flowing into your extruder, and you have one die opening that's 3 millimeters, you could have 20 pounds a minute coming out of that die opening. So the pressure increases. So for all of you that have had thermodynamics, okay, the ideal gas law says that when you have a high pressure on one side of a restriction and then it's released to the atmosphere, this pressure differential is going to cause an expansion. And that's what we typically see when material comes out of an extruder die. That's what gives us a porous texture. So if you take a look, this is a single screw laboratory scale extruder, not a lot of pressure, not a lot of expansion. Okay? This is the discharge of a Wenger, a little higher flow rate. There's a little bit of expansion, but not much. Now this is when we turn the cutter head on, put the guard in place so we don't cut our students' fingers off, then we get better expansion, get the products that we typically think about in terms of pellets. So the die opening is key, it's critical. You can make all sorts of shapes. Typically what we think about is little round pellets, whatever millimeter size that we want to buy from Silver Cup or Rengen or whoever we're going to buy the pellets from. But you can make all sorts of things. So common type of extruder is the single screw. Okay? But there's also twin screw extruders that are available. Now, if you have a twin screw extruder, the screws can be rotating together or rotating opposite of each other. What's the advantage? This type of this type of extruder, the counter-rotating, actually gives you better mixing capabilities because those ingredients are pushed into the opening, into that space between the screws. This type, where you have them rotating in the same direction, does a better job of conveying, but not so much in terms of mixing. So you can think about laboratory scale extruders, which are great for experimental diets. A lot of experimental diets are made with like a Hobart sausage grinder. The thing is, you don't get any temperature increase with those. Or if you have KitchenAid mixers, you can also get the sausage grinder attachment for your KitchenAid mixer. But you don't get any cooking, any temperature increase. So pilot scale extruders, we've done a lot on the Wenger system. Gives you a lot better flow rate, a lot better temperature control. But then you have the commercial scale. You think of the feed mill side. Okay, the feed mills generally going to have larger systems than the pilot scale systems. So when you think about extruders, the screws of extruders, single screw or twin screw, you can either have a continuous single element, kind of like this really small scale extruders have, or if you're looking at pilot scale or commercial scale, basically, what element do you want? They come in pieces. And they're bolted together on a shaft like this. So in this case, we have a counter-rotating. And if you take a look, you see we have elements and then we have interruptions. Those interrupted areas are where we're actually adding steam. And so these steam locks give us a chance for that steam to work into the ingredients. So single screw, twin screw, single element, multiple elements. Okay, temperature control. Do we let friction handle it for us? Which is the InstaPro approach. We call that an autogenous. It's an automatic temperature increase that we don't control because it's due to friction. Or isothermal, which basically we have heaters, we have cooling jackets, we try to control the temperature at a constant rate along the barrels. This isn't used very often. More often than not, what's typically used is we have external heat, which is band heaters. We have friction, and then we have some type of water jackets. So common conditions: low moisture, medium moisture, high moisture. When you think low moisture, you think generally less than 20%. Okay. How many of you like to eat Cheetos? Only two people. All right. Cheetos are fantastic. It's extruded corn with cheese sauce sprayed on it. But the thing is, when you have low moisture, that starch does a better job of expanding. So typically you think of low moisture for human foods. Medium moisture, often we see this in extrusion. High moisture, generally more than 30%. Just so you know, if you're making your own feeds, moisture is not temperature is important, but moisture is as important as temperature. Water can do some really interesting things in terms of binding. So if you want to have pellets that don't degrade in water, increase your water stability, increase your moisture content when you're making your pellets. That's one of the things that you don't hear very much about, and it's really underrated. Moisture is critical. Now, granted, you have to dry your pellets a little better so that you have an extended shelf life, but water is critical for water stability. So what kind of speed do you want to use? Low speed, high speed, or medium speed? Generally, the small scale, lab scale extruders are going to be low speed. Pilot scale are going to be medium, and then commercial scale are generally going to be your high speed extruders. Higher speed, higher capacity. So when you're making feeds, we need to think about a lot of things. It's kind of like the circus. How many balls can the jugglers keep in the air? Okay, you need to think about your raw ingredients, you need to think about your processing conditions, and you need to think about your final products. So when you buy a feed, whether it's Silver Cup or whatever, what's one of the first things you do? If you want a floatable feed, you throw some in a cup, right? And see if it floats or if it sinks. Or if you're making your own feed, that's what you do. But you also want those ingredients to be available to the fish. You don't want those ingredients to be degraded. So just because something is at 34% protein, doesn't mean that it's equivalent to something else that's 34% protein if one actually is denatured or not. So things to think about. So when we think about our raw ingredient properties, okay, of course, amino acids, fatty acids, protein, fat, fiber, ash, the whole compositional aspect. Okay, we also need to think about particle size distribution, because when you are blending a feed, if you're using DDG or using soybean meal or soy protein concentrate, those ingredients are going to have different particle sizes. And when you put them together in a mixer, you move those blends out of the mixer, you're going to have particle segregation. So you're going to have concentrations, or you might have, let's say you have some of the soy protein concentrate or soy protein isolate. That stuff absorbs water, so it tends to clump. So basically, how do you deal with particle size distributions? Outside of the US, the feed mills have it figured out. They do a post-mix grind as opposed to the grinding before mixing. Most of the feed mills in the US are set up, they grind their ingredients separately, then they mix them, then they pelletize. Elsewhere around the world, it's the opposite. You mix everything together, you grind everything together, then you pelletize. That does a much better job in terms of ingredient distributions. So hopefully the feed industry will catch on to that sometime in the near future. But if you're making your own experimental diet, something to think about. Moisture content's important, and color is becoming more important as a quality control measure, especially with the ethanol companies and their distillers' products. They're using the LAB score as an indicator of quality at the ethanol plants. Now, it's debatable whether LAB actually correlates to amino acid digestibility, but there's some evidence that it might to some degree. But at least it gives them a quality control tool. So when we look at the extrusion processing conditions, okay, the size, the shape, the geometry of the pellet is important. The distribution of temperature through the extruder is important. Die pressure basically defines how much expansion you get as that pellet comes out of the die. Okay, the viscosity and the density of that dough as it's exiting the die. Basically, it's a liquid that's coming through that die right before it expands. So we need to be able to control that. How much energy do we put into this extruder? Typically, the more energy you put in to turn that shaft, the more frictional heat you're going to have. Water, steam, how much you add, whether it's just the conditioner or both the conditioner and the extruder. And ultimately, from a processing side, what's your throughput? How fast can you get product made? So when you look at your extruded pellets, what kind of changes do you see in composition? Not just gross composition, but digestibility and availability to the fish. Moisture content and water activity of the pellets. Typically, you're going to have to dry these because you've added water during the processing. Color changes. Okay, generally, when you have a heat treatment of feed ingredients, you're going to see a darkening of those ingredients. Sometimes that's due to denaturing the proteins, and sometimes it's not. What diameter are you looking for? What kind of expansion do you have? What kind of floatability? What kind of water absorption does that have when you put the pellets in water? You don't want the pellets to absorb water too quickly, because when that water starts to infiltrate that pellet, it's going to start to break the pellet down. And then the pellet is just going to become waste on the bottom of your pond or your tank. So, all right, so let's talk about theory. So, we've talked about the basics. Now, the theory is, theoretically, what happens is, as you put raw ingredients in the introduction area of the extruder, basically you have discrete particles. Whether it's DDG or corn or soybean meal, you have discrete particles, and then as that material is conveyed down the extruder, they start to melt until finally, right before exiting, they're a liquid. So starch is key. Starch is the glue that holds the ingredients together as they exit out of that die. So what we want to do, as you're manufacturing feed, you want the starch to break down, because initially starch is globular in structure. So this is at 60 degrees. At 80 degrees, we see this network, this glue will surround all of the other particles and hold them together in a matrix. So we want the starch to melt. The glue, basically, it allows water and other materials to bind to the starch molecules. So typically, when you're extruding feeds, you need to get above 90 degrees Celsius in order for that starch to gelatinize. And depending on what starch you're working with, whether it's a rice starch or a corn starch or a potato starch or other starch, you may need to get above 100, 110. So what starch does as it melts, and as the other ingredients melt, we need to think about viscosity. Because when those ingredients become liquid, they flow. Now, when you think about viscosity, basically viscosity is thickness of the fluid, or the ability of that fluid to flow. So this line right here is what we call a Newtonian fluid. Okay? A Newtonian fluid basically means the faster you push that material, the viscosity is not going to change. Okay? Water, oil, those are examples of Newtonian fluids. Okay? So the slope of this line, okay, speed or rate of shear and shear stress, okay, the slope of this line is constant. The viscosity is constant, no matter how fast or how slow you push that liquid. Now, there are all sorts of liquids, fluids in this world, and most feed ingredients are what we call pseudoplastic. Okay, the faster you go, you're going to get an increase, and then it's going to level out. Okay, so the faster you go, the easier it is to push that fluid. So the slower the flow, the more resistant, the more energy it takes to move that fluid. So basically, if you take a look at viscosity, this is speed, viscosity decreases non-linearly the faster you move that extruder screw. So viscosity changes not just with speed but with temperature. The higher the temperature, the lower that viscosity. So that impacts your flow rate through your extruder. And basically, what pushes that material through the extruder? It's the friction with the screw and the resistant friction against the extruder wall, the barrel wall. But it's also the pressure that's building up. It's also pushing that material along. So the best way to quantify your flow rate is your mass flow rate divided by your density. The density of those pellets. So how do you measure flow rate? You put a bucket outside the discharge of the extruder. That's the best way to measure flow rate. So energy consumption is also important. Okay, basically you have the energy that your motor provides, your mechanical energy. How much does it take to turn that screw and push that material? If you are adding heat to surrounding jackets, okay, you've got to account for that. And if you're adding steam, you have to account for the latent energy in the steam. So energy is a measure of, well, we worry about energy because we want to, from a processing standpoint, minimize the energy consumption but maximize our product characteristics. So if we want to quantify energy consumption, okay, this is how you quantify energy consumption. It depends on your geometry, your speed, your temperature, your material characteristics. You know what? I don't want to do that. All right. You theoretically can measure the heat that you add, the electricity that's added to your heaters. You can measure the steam flow rate. But by and large, what really is used, if you have a power meter that you can plug into your extruder and measure how much energy that extruder is consuming, that's the way to do it. So you measure it with one of the three-phase power meters, which you can get for about $2,000. Now, they used to be a lot more expensive. So you measure that. Here's your power consumption. Divide it by your mass flow rate, which you measured with your bucket. And this gives us what's called the SME, specific mechanical energy. How much power per kilogram or per pound. So the more power it takes to push that material through, the more energy you're adding into the friction, into the heating. So this is an example of what I'm talking about. So last year we plugged a three-phase power meter into our extruder and started the extruder up. And basically, if you don't add anything any ingredients, you're going to have some type of a power consumption just due to friction to turn that screw as that screw interacts with the bearings. Okay, so you're going to have to, this is friction that's not doing any work for you. What you care about is this stuff right up here. So when we started dumping the ingredients in, okay, power consumption increased because we're trying to move that material down. We hit a hanger bearing, so this is chamber 1 or zone 1. The trajectory of that power increase changed. We're filling zone 2. Hit another hanger bearing, entered zone 3. So this is, we didn't run the experiment very long, but this is the effective power consumption as you're moving that material when that extruder's full. And then as the barrel started to empty, then it would decrease. So this is the area, the sweet spot, if you will, where you're processing. This is your power consumption. So competing effects. Talked about a lot of things, but the juggling act is what we're trying to really worry about. If somebody says, I can't get my pellet to have floatability of more than 10 seconds or 20 seconds, or my pellet's not water stable, okay, let's go tweak something in the process. Well, you change one thing, everything starts to fall apart. So basically, as you increase your screw speed, your viscosity is going to go down because it's shear thinning material or pseudoplastic material. As your screw speed increases, your SME is going to increase because it takes more energy to turn that screw faster. Your expansion should increase. Now, I say should because this isn't always true, but your expansion should increase because of the increase in temperature, because of the increase in friction. And of course, the faster you turn the screw, the faster you should have throughput through your extruder. So, keeping everything else constant. As you increase the temperature, if you have band heaters or you're adding steam, viscosity should go down as temperature increases. Okay? Your SME should go down at the same screw speed because your viscosity is going down. Okay? Your expansion should go up because you have faster, greater water evaporation at the die exit. So temperature is critical. Water is critical, but so is temperature. So if it's too low, you're not going to cook your product. If it's too high, you're going to denature your proteins, make them indigestible, or you're going to make glass. Okay? So this is a biological form of glass. It's the proteins which have been denatured, and I tell you, the folks that I was working with were not really very happy because we had to pull that extruder apart bolt by bolt, and it took about 6 hours to take that extruder apart and clean it out. You don't want to make glass. You want to be somewhere in the middle. You gelatinize your starch, you have good expansion, you have good particle melting, and you have good pellet cohesion. Okay? So another thing to think about. As materials move through an extruder, okay, we talk about denaturing proteins. Temperature has an effect on proteins, amino acids, vitamins, antibiotics, enzymes, yeasts. Any biological material is going to degrade with temperature. So, and the higher the temperature and the longer the residence time, the more degradation you're going to have. So ideally, what you do, shut the temperature off, let the material flow through the extruder so there you minimize your temperature increase, but that trade-off is you're not going to have expansion, you're not going to have cooking, you're not going to have gelatinization. So how do you get the right answer? It truly is a juggling act because you need some temperature to get the job done. But you don't want to totally degrade the materials that you're trying to transport to the fish. So keeping everything else constant. As you increase your moisture content, your viscosity is going to decrease, which is good. Your SME is going to decrease because that viscosity goes down. But your pressure drop is going to go down, and theoretically your expansion is going to decrease too. So it's a trade-off. But your cohesion, your water stability is going to increase. So if you're having trouble with producing a pellet that's stable in water, increase your moisture content. That's the first thing I would tell you to do. So too low, your pellets aren't going to bind. Too high, you're not going to get enough cooking. Okay, so you need to be somewhere in the middle. Oh, also if you have too high moisture, you're going to plug your extruder or you're going to plug your other machines. So somewhere in the middle is where you need. As your die diameter goes up, if you use a 3 millimeter versus a 2 millimeter, or a 4 millimeter instead of a 2 millimeter, and why would you want to do that? different size fish. So obviously your ingredients are going to change to some extent, but as your dye increases, your pressure drop is going to decrease, your SME is going to decrease, and your expansion is going to decrease. So you're going to have to change something else in the process. So a lot of competing effects. So something to think about. Particle size is key. We haven't talked about particle size yet. We talked about the distribution, but if you do a post-mix grind, really you need to have the particle size less than 0.5 millimeters. The smaller the better in terms of extrusion. Otherwise, if you don't grind your ingredients properly, you're going to have stress fractures in your pellets, or the pellets aren't going to bind at all. You're going to have poor durability, or you may plug your dye. If you're producing a diet with fish meal and you're doing a 3 millimeter diet, if you don't have your particles ground fine enough, you may plug your dye with bone fragments, depending on the quality of the fish meal. So, competing effects. Are we getting close on time? Okay. Everyone wants to eat lunch. So, fiber is important, oil is important, and protein is important. Okay? Fiber doesn't really like to play ball with the other team players. So, it doesn't really like to react. It likes to absorb water. It likes to decrease your pellet quality, but it doesn't really like to play. So the best way to deal with fiber, if you have to deal with fiber, is to do a really good job of grinding those ingredients. Okay? Oil is a lubricant. Oil makes extrusion a challenge, especially for smaller diameter pellets. So if you need to add oil, my suggestion is do a post-extrusion coating. Either a vacuum coating or other type of coating. That's my suggestion. Protein, high protein blends don't expand. That's why the starch is critical. So if you have a high protein blend, increase your moisture or change the type of starch that you have. So a few examples of what we would consider, visually anyway, as a high quality pellet. They look good. Do they perform good? I don't know. We'll have to see. Actually, these all did perform very well. But same composition, this is what I would consider poor quality pellets. The pellets are falling apart. They don't have cohesion. I think I'd much rather have these type of pellets than those type. So floating feeds versus sinking feeds. The challenge is to make whatever feed impervious on that outer shell to water penetration. Otherwise, you're going to get basically crumbles on the bottom of your tank or your pond. So, a little perspective. So, we talk about making high quality feeds using extrusion. You can make a lot of feed with machines that are not as fancy as we have here in the US. This is an example of some work I'm doing in Bangladesh right now. There are over 1,000 of these small-scale extruders. No temperature control, no water injection, no steam injection. Basically, you blend everything up by hand and dump it in. And then you set it out on a concrete pad to air dry. Okay, now, granted, the pellet quality is more like this than this. So, trade-offs.